vLLM turns any GPU you already own into a real OpenAI-compatible API, serving dozens of users at once, with continuous batching under the hood. Ollama can't do that. vLLM is not a laptop chatbot tool. It's Linux only from the project itself. No native macOS GPU backend, no double-click GGUF loading like Ollama or llama.cpp. Windows means WSL, or an unofficial fork. What vLLM does is continuous batching across many simultaneous requests on an NVIDIA or AMD GPU, squeezing maximum throughput out of hardware you already own. If you're one person asking one question at a time, stick with Ollama. If you're standing up a real API endpoint for multiple clients, this is the right tool instead. Version numbers move fast here. 0.25.0 shipped July 11th, 0.25.1 patched 3 days later on the 14th, and 0.26.0 landed today, July 25th. That's 3 releases in 2 weeks. Python support spans 3.10 to 3.13, with 3.12 recommended and required outright for the ROSEM pre-built wheels. If 0.26.0 turns out rough by the time you watch this, 0.25.1 is the safe fallback. Same API surface, 1 release back. Getting it running takes 3 lines, assuming a real NVIDIA card. Spin up a virtual environment with UV, targeting Python 3.12, the version the docs actually recommend, even though 3.10 through 3.13 all work. Install vLLM with the CUDA backend detected automatically, which pulls in the matching PyTorch and CUDA wheels. No UV on your box? Plain pip works too, pointed at PyTorch's own CUDA 12.9 wheel index. Either way, check the version once it lands. Now start the server pointed at Qwen 2.57b instruct, an ungated 7.6 billion parameter model with no license click-through to slow the demo. Cap context at 8K tokens, tell it to use 90% of GPU memory, force bfloat 16 precision, and require an API key so nobody else can hit this box. 2 flags worth knowing even though this demo skips them. Tensor parallel size to shard one model across multiple GPUs, and quantization to load an AWQ or GPTQ checkpoint instead of full precision. The log ends on UVcorn running on port 8000. The server is live. Every request needs a KV cache, memory that grows as generation goes. Naive serving systems reserve a worst-case contiguous block per request up front. vLLM's own launch numbers put the waste at 60 to 80% of memory from fragmentation and over-reservation. PagedAttention splits that cache into fixed-size blocks that don't need to sit next to each other, the same trick as OS virtual memory paging, with a block table mapping each sequence to its scattered physical blocks. Requests can even share blocks for a common system prompt through copy on write. Waste drops to under 4%. Static batching runs a fixed group of requests together and waits for the slowest one to finish before starting the next batch, so finished requests just sit idle, holding a seat, wasting GPU cycles the whole time. vLLM's scheduler instead adds and evicts individual sequences at every engine step. The moment one request finishes, its slot goes straight to a new arrival. That only works because PagedAttention already made room non-contiguous, so slotting in a new sequence mid-batch is cheap. CUDA is the mature path, pre-built wheels shipping CUDA 12.9 binaries. Blackwell cards need at least CUDA 12.8. AMD ROCm covers MI200 through MI350 and the Radeon RX 7900 and 9000 series, needing ROCm 6.3 or newer. Intel's XPU backend handles basic inference on data center GPU and ARC, still work in progress. CPU serving works on x86, ARM, and even IBM Z mainframes. Apple Silicon GPU acceleration is not vLLM at all. It's a separate community plugin called vLLM Metal, running on MALX, not vLLM's own kernels. vLLM's own 2023 launch benchmark, run by the PagedAttention paper's authors, is still the number people quote. Tested on Ollama 7B on an A10G and Ollama 13B on an A100, Against plain Hugging Face transformers, single completion throughput ran 14x to 24x higher, and 3 parallel completions ran 8.5x to 15x higher. Quick note, I do this daily. Subscribe if that's useful. Against Hugging Face's own TGI server, the gap was smaller, 2.2x to 2.5x for single completions, 3.3x to 3.5x for 3 parallel completions. Call these vendor numbers from 2023, not a live daily benchmark. Still, even the smallest number here, 2.2x over TGI, is real throughput most teams never bother to capture. Here's the payoff. A real HTTP endpoint, not a Python-only interface. A plain curl request with a bearer token hits /v1 chat completions, same shape OpenAI's API expects. It answers who won the 2020 World Series, valid OpenAI format JSON back. The same server also speaks embeddings, audio transcription, the newer responses API, and tool calling with a response format parameter for structured output, so most OpenAI SDK code just works unchanged. Tool calling has one wrinkle. Setting parallel tool calls to false caps the model at 1 call per response. Whether it can return more than 1 at once depends on the model's own parser. The trick that matters for existing code, point the OpenAI Python client's base URL at your own box instead of the default, keep everything else the same. Set the API key to match whatever you passed on the server. Call chat completions exactly like you would against GPT, asking it to explain PagedAttention in 1 sentence. And every app you've already built against the OpenAI SDK, LangChain included, now talks to hardware you own instead of a bill from OpenAI. Numbers on your own hardware beat any benchmark I could quote. Run vLLM bench, serve against the OpenAI-chat backend, pointed at the same server, 200 prompts, capped at 32 concurrent requests to simulate real traffic instead of firing everything at once. The dataset defaults to random length prompts, but ShareGT and BurstGPT traces are built in too if you want something closer to real chat logs. No pre-baked number here. Whatever throughput and latency percentiles print out on your GPU is the real answer for your card and this model. Watch requests per second and time to first token. Specifically, those are the 2 numbers that tell you if this setup actually holds up under load. BFR16 weights for this 7.6 billion parameter model run about 15 to 16 gig. A 24 gig card has room to spare. 3 things separate a demo from something you'd actually run. First, auth, pass an API key flag, or the server accepts anyone. There's no auth on by default. Second, scale, vLLM's own nginx. Example load balances multiple instances with a least connections algorithm. Third, ops, the official Docker image is vLLM OpenAI, and a /metrics endpoint exports Prometheus series, including one that tracks live KV cache usage %, the exact mechanism from the paging diagram earlier, now visible as a number climbing on a dashboard, while real traffic hits the box. Skip the API key and put this on a public IP, and anyone on the internet gets a free inference server. Push max model N past what the KV cache can actually hold, and vLLM does not fail quietly. Request a context window bigger than the reserved cache blocks, and you get a hard value error. The model's max sequence length is larger than what fits in the KV cache. Try increasing GPU memory utilization, or decreasing max model N. The fix is exactly what the error says. Drop max model N back down, or raise GPU memory utilization toward its 0.92 default. That's the honest version of this tool. Real limits, real error text, not a sanitized happy path demo. Ollama wins for 1 person on a laptop. 0 setup. vLLM wins the moment you need concurrent throughput on a real GPU. Pick based on how many people are hitting that endpoint at once, not which tool sounds cooler. vLLM won't replace Ollama on your laptop, and it isn't trying to. It replaces the moment you'd otherwise be writing your own batching queue in front of a GPU. Clone the quick start, point your existing OpenAI code at your own box, and go measure your own throughput instead of trusting mine.